But thank you all again for coming to Energy Talks. My name is Valerie. I use the pronouns she and her. I'm the Outreach and Engagement Lead at Future Energy Systems. I know some of you have heard of Future Energy Systems because you've been here before, or you are a grad student at the U of A in Future Energy Systems. But just for anyone else, Future Energy Systems is a research program at the University of Alberta, which receives $75 million from the federal government to explore the energy transition. Everything from air and water and land and cleaning that up to energy technologies to the economics, political, all of those different aspects of the energy transition. And before we dive into our talk tonight, we want to acknowledge that the University of Alberta, and tonight, we are located on Treaty 6 territory, and this is a traditional gathering place for many Indigenous peoples, including the Cree, Blackfoot, Métis, Nakota Sioux, Iroquois, Dene, Ojibwe, Saulteaux, Anishinaabe, Inuit, and so many others that continue to influence our vibrant community. We also want to acknowledge all the communities and peoples on the lands that we do research on. We don't just study in Edmonton, we do research across Canada and in other countries. We want to acknowledge all of those Indigenous peoples as well. So tonight you're going to dive into one research area in Future Energy Systems, but we also have over 150 researchers, over 100 research projects, and over 1,000 graduate students who make our research possible. For the purpose of the tape, we want to remind current and future viewers that the opinions expressed by the speaker may not be those of the University of Alberta, Edmonton Public Library, or Future Energy Systems. But now that that is all out of the way, we are going to invite our amazing speaker up tonight. Maricor Arlos is an assistant professor at the University of Alberta in civil and environmental engineering, who specializes in tracking, fate, and transport of contaminants from municipal wastewater, industrial activities such as the oil sands, and agriculture. She currently serves on the Scientific Advisory Committee for Pest Control Products, offering independent scientific insight to Health Canada's mandate on pesticide use.
Hello everyone, thank you all for coming, and thanks for my grad students for showing up. I haven't had a chance to chat with them. It was such a busy semester, and then we went out for dinner before we got here, so it's really nice to have that community. So my talk for today is H2O, emerging water contaminants in our urban environment. So Valerie already did a land acknowledgement. I do want to have my own personal land acknowledgement. I am a Filipino settler. I've been here for 19 years. My family moved to Canada 19 years ago. And this place really was very important in my journey and my deep connection to water. So I recognize a lot of the teachings from many Indigenous peoples, not only in this Treaty 6 territory, but all across Canada, for inspiring me and motivating me where I live and work. And I live in Edmonton, Treaty 6 territory. So just a little bit of story about myself. I always like to connect water with my personal journey because it's really such an important part of my life. I was born and raised in the Philippines. Philippines is an island of, it's an archipelago with 7,000 islands. I was surrounded by water, but really never felt that connection to water when I moved to Canada. That's when I studied environmental engineering, did my bachelor's and master's there, and I did my PhD in biology. I'm not a biologist. I consider myself as an environmental engineer, but I work a lot with biologists. The reason that was very profound was that's when I realized, I think growing up in the Philippines, I was surrounded by water, but I never really understood and cared for it. Understood the importance of water myself. And I never knew that water treatment plants exist because we don't have a water treatment plant at home. We get our water from the ground, and eventually we got connected to a treatment facility. I even asked my dad, where did your go when I flushed the toilet? Because I learned in class that it goes somewhere else. So we have a different water or wastewater system in the Philippines. And that encouraged me to look into what water truly means, I see a lot of the Canadians really take care of the waters way better than the Filipinos back home. It's just, there's so many different reasons why. There's colonial history in the Philippines that also impacted that. And when I started working with learning more about water, the deep connection, the relationship with Indigenous peoples even created a profound change in the way I see water. So I spent 11 years at Waterloo. I moved to Switzerland, elsewhere, to figure out, how other parts of the world value water. And 3 years ago, March 14th, 2020, I flew literally during COVID when everything shut down. I was on the plane from Switzerland to Edmonton. As a baby prof, I now call myself a teenage prof. I don't think I can use the baby prof term anymore. And I feel that I have a platform to make contributions for the community and also deepen my connection to water. So I try to instill that with my students as well. So in terms of my research, I sort of group them in 3 general areas. The water quality management is where I was trained as an environmental engineer, which I'm going to talk a lot more about today in terms of the micropollutant fate and transport. I'll tell you more about micropollutants later. I also look at sustainable treatment approaches. I am an engineer, so I look for solutions for water issues. And then more recently, actually the last year, I tried looking into ecological production and working with Indigenous peoples and really trying to interweave the Indigenous knowledge and also the Western knowledge that I learned as an undergraduate, graduate, PhD student, and now as an assistant professor. It's really tough. It creates a lot of emotional labor, but it's really fulfilling. I'm not going to talk about that. I'm going to talk about the fate and transfer of micropollutants in our urban water systems and their impact on exposed aquatic organisms. So what are micropollutants? So micro, small, baby pollutants, and they are very diverse. They could be pharmaceuticals, personal care products. They could also be natural and synthetic hormones, and it can be pesticides and industrial chemicals. So these are compounds that are found in the environment at very, very low concentrations. If I say low concentrations, I mean parts per billion to parts per trillion. So for those who want to visualize parts per billion, think of a beaker with 1 billion beads, and one of them is peach-colored. So one peach-colored bead among the 1 billion is 1 part per billion. And of course, one peach-colored bead and 1 trillion beads means 1 part per trillion. So you can just imagine the drop in the lake type of concentration that we're dealing with here. So why bother when they're present at low concentrations? This is sort of my journey as a grad student, a master's student. That's when I started working with biologists. What they found is that antidepressants, they don't usually get synthesized by our bodies 100%. So they end up in wastewater. If they're in the wastewater, they're not necessarily treated. So they end up in our aquatic ecosystems, and they can bioaccumulate in fish. So some studies have shown that antidepressants can actually be present in brains of big fish brains. Antidepressants can also affect anxiety-related behavior. So think about fish who's really aggressive, right? Because they need to fight it's part of who they are and what they do, and they want to be aggressive because that's their territory. What they found is if they've been taken antidepressant, they tend to be less aggressive. So then it reduces their potential to survive because now they have small territory, or they don't have opportunity to interact with others, or at least look for a mate, right? Another interesting thing, if antidepressants can make them chill a little bit, crayfish, when exposed to antidepressants, they became more aggressive. So a lot of the aggressiveness is a bit of a problem for crayfish, because what happens is if they have some predator, instead of them hiding, they tend to get out and fight that predator. So if you, crayfish, want to survive, you obviously want to hide and not fight the predators. I don't know if this video is going to play. So this is just a video from research from University of Florida. So they just show how the aggressiveness, once exposed to an antidepressant, they tend to become, the crayfish become more aggressive. And I found that on Twitter and I thought it was really nice to share that with everyone. So I thought that was interesting that these antidepressants can have different types of impacts. It can make fish chill out, or it can make crayfish really, really aggressive. One thing that was close to my, one of the terrestrial impacts related to micropollutants is the vulture population collapsed by 90%. So diclofenac in South Asia, diclofenac is an anti-inflammatory. And actually, when I started researching, I now look at like what are the active ingredients in the medicines or drugs that I take. So diclofenac is an anti-inflammatory, and then they introduced that to South Asia cows to treat colic. So when they basically die, and you have some carcasses there, the vultures feed on the animal carcasses, and what happens is the diclofenac that's in their system gets transferred to the vultures, and what they notice is the population collapse. And then when they banned the diclofenac use for cows or for cattle, the population starts to get back up. So this is just a simple drug to treat, like basically an anti-inflammatory drug, creating the population collapse. This is sort of the area where I did my master's and PhD on. And it started out with this researchers finding out that 5 parts per trillion, so we talked about 1 part per trillion, so now it's 5 parts per trillion, ethanol estradiol, which is a major component of birth control pill, can actually cause the collapse of a fish population. So if you are not from Ontario, Ontario has experimental lake systems, so these are pristine lakes that you can do some experiments. You can dose the lake with certain types of chemicals to see the impact of the population level. So this experiment was conducted by Karen Kidd and dosed this lake with 5 parts per trillion ethanol estradiol, which is a birth control pill ingredient. And what they found that it feminized fish. So this is what we call fish intersex. So male fish becoming female. So this is just a microscopic picture. This is the male testes, and you see some eggs there, oocytes showing in male fish. So she tracked down, this is one of the earlier studies related to population collapse. She tracked down the population from 1999 to 2005, so 6 years of data sets. So this is the control lake, and you see healthy population of lake. But after 2002 or 2001, when the pill was introduced into the lake, you see population collapse. In other words, you don't see any babies anymore, so you're not making babies. So if population does not proliferate, then they might be wiped out, and that might impact the ecosystem. So this sort of interested me when I was a master's student 10 years ago now, and what the work that the Servos Lab Group, which was where I was trained, they collected fish upstream and downstream of a wastewater treatment plant. And this is the male testes, very healthy, white, good looking, good male, very handsome male. And you find a fish downstream, also very beautiful from the outside. You can actually see eggs forming in the male testes. So I thought that was really crazy. I'm like, why is this happening? Male fish turning into female. So why does that happen? So I just wanted to bring everyone back to our urban water cycle. So it's slightly different from the water cycle that you learn in class. It's got some other parts to it. So for us here, we get our water from some sort of river, source water, groundwater, lakes. It goes through water treatment. it gets to the distribution. We all use water. Everyone showered this morning. At least wash your face, right? And then because of that, you end up creating wastewater. And then you have a centralized system where you collect it into sewer pipes, goes into a wastewater treatment, and then it gets discharged again into the receiving environment. Clean enough that it's okay and safe to be discharged into the environment. So that's the idea of wastewater treatment. So this is how our cycle goes. And when you discharge it, not back to the same place where you get your water, you discharge it many kilometers down the street. So you're not gonna impact your source water. In terms of the fish population, or fish intersects, wastewater effluents are a main source of micropollutants. One of the main sources of micropollutants. So just imagine this morning, you wash your face, you use some personal care products. You probably took some, one medication if you got a headache, right? And not all of that is going to be metabolized by the body, goes into your wastewater. And our wastewater treatment plants are not designed to treat pharmaceuticals and personal care products. They're designed to treat something else. They're designed to treat organics, but not necessarily these compounds that are found in really, really low concentrations. So what is a wastewater treatment plant? I thought I'd just kind of walk everyone through. So you use your waste. When I ask my students, where does your water go after you flush your toilet, most of them would say, it magically disappears. I don't have to worry about that. But that's not really the case. It goes through a series of sewer pipe systems, and then we get to deal with fats, oils, grease. So just imagine, if you have bacon grease, you pour it over the sink, it's going to go into our wastewater and actually clogs up. Things that are flushable, that are not really flushable, they don't really degrade in our wastewater. So there's that headworks to get rid of all of those stuff. And then it's going to clear that water up a little bit using primary clarifier. It's really a settling tank. And then it goes into this, we call them bioreactors. And there's so many research in terms of how that can be configured. But ideally is you have microbes in there that would eat up all of those organics, and that they use that as their food. So it's a biological treatment. And then you clean that, hopefully they use that now as their food source, so then obviously that gets converted into either simpler products, and that goes into a secondary clarifier. You want to clean that up a little bit, and you have some polishing steps here in the gold bar wastewater treatment. This is not gold bar, this is just, I think, another one from the States. They would use UV disinfection to deal with different types of bacteria that can come from the biological treatment as well. And then it goes into the river. It's clean enough. It's okay for environmental health guidelines and regulations. So that's what a wastewater treatment plant, and hopefully you have the environment to kind of treat it and dilute it and make sure that they are removed from the system. You have a community somewhere downstream, which is the problem of Calgary right now because there's really huge urbanization. That's what I'm going to talk about today. You can have another community building here, right? And you don't know what the source water is like because they've already received wastewater from upstream. So right now, Edmonton, we're pretty good. Our North Saskatchewan River is quite large to deal with our wastewater, but if you think about 2-3 decades from now with the population increase and the new development is something that really we have to think about. So that's wastewater treatment plant 101. If you think about municipal wastewater treatment systems, it differs in Canada. Alberta is one of the really advanced provinces for water treatment. The reason that we see those fish intersects downstream of a wastewater treatment plant, forgot to tell you that was from Kitchener wastewater treatment plant in Ontario, in the Grand River watershed. It's because they don't have the advanced treatment system. And what studies have shown with advanced treatment systems, in other words, you have good biological treatment removal, you have some UV disinfection, they can deal with those micropollutants really well. So if you think about Alberta, most of our treatment systems are tertiary treated, really good. If you look at Ontario and Quebec, only a few, but most are secondary treated. And some of them don't have any treatment at all. So can you imagine? And BC also has some of those places that don't have wastewater treatment plant. So they always think the East and the West Coast, you have the Pacific Ocean and the Atlantic Ocean. Solution to pollution is dilution. That's not what we want to teach, or that's how I was taught as an environmental engineer, but the mindset regarding water treatment has changed too. So solution to pollution is dilution. So if you have a big ocean, you can just dump raw sewage in there and dilute it, right? I don't particularly like that. But we're good here in Alberta in terms of our wastewater treatment systems. So I'm going to take you to sort of a case study of the work that I've done, a collaboration with the City of Calgary and a few researchers at the University of Calgary. And Calgary has 3 wastewater treatment plants. We only have 1 here. And the 3 treatment plants discharges into the Bow River. So this whole section is the Bow River. And the Bow River basically goes all the way from, it gets its water from the glaciers. It's a glacially fed river system. And there's a few towns and settlements upstream of Calgary. And it goes through, the wastewater goes through, enters 3 wastewater treatment plants, the Bonnie Brook wastewater treatment plant, Fish Creek, and then Pine Creek wastewater treatment plant. So this whole line here, or the shaded region, is the City of Calgary boundary. So they get their water from here, the Bow River, in the Bear Spa Reservoir, and then they also get their water here too, which is the Elbow River Glenmore Reservoir. So as you can see, the water travels from northwest to southeast. It would basically receive many types of inputs, including stormwater outfalls, different types of things. Basically the idea that here at BR4, this downstream site, it's cumulative impact of everything above it. So what they did, they monitored all of the sites in red, and also all the sites, the wastewater treatment plant, and looked at the trends in their micropollutants concentrations over, and they're still doing it now, but they started in 2018 really for big scale monitoring. So I just wanted to provide a little bit of information of why they do that. They're getting a lot of questions when I talk to Norma, who's the City of Calgary Water Services operations manager. He would always say, I get calls from public saying, is there pharmaceuticals or antidepressant in the water? So they didn't know at that time how to answer, so they decided, okay, let's look at the monitoring approaches. They also they think of slightly different in terms of, first of all, they're in a watershed that's really under a lot of pressure. So there's going to be a lot of activities north of it, a lot of potential for urban development. So they want to make sure that they protect their water. So it's slightly different from what we have here in the North Saskatchewan River. But first they want to ensure that the public health is protected, the concentrations are low enough, but it's not going to create any issues. There can be new guidelines and regulations, and then once they know what's in their system, they can figure out what type of treatment they need in order to lower certain concentrations to a certain level. And they really want to be this industry leader for emerging contaminants. They have a very expensive instrumentation in-house to measure these contaminants. And these can cost up to $1 million. And they basically run almost every day. It's fully functional. And they're willing to invest that much money, which is really, for me, is very forward thinking, really, for any type of water utility, because that's such an expensive investment. But so, as part of our collaboration, they started in 2015. They looked at small groups of micropollutants, and then in 2018 they started monitoring 55, and I'll tell you what those micropollutants are. And I have this really expensive fancy instrumentation that was online, And then they started looking at all of those sites as a whole now that they have that methodology to monitor and measure these contaminants. So these are just the folks that I work with in the city of Calgary. They're very gracious and trusting in terms of giving me their data sets. They're really wonderful people, and I have a few, one student, Seth Umagat, who helped out with the analysis work, and then the PI for this project is Dr. Kelly McPitrick from the University of Calgary. So they have 4 years of monthly data. They have 55 compounds, and I'll tell you what these compounds are, 14 sites, and you can easily add up the data points, 21,000 data points. And at that time, they're like, we don't know what to do with this. Help us to find, we got this fancy machine, we don't have time to look at all data sets. Can you help us? Together, can we come up with some of the trends to help us design our future monitoring program? So these are the categories of their compounds. So you have pharmaceuticals, you have cardiovascular drugs, antibiotics, antidepressants, analgesics, antidiabetic, neuroinhibitors. You also have industrial chemicals, so antibacterial agent, cotinine, you have flame retardants, insect repellents, plasticizers, all kinds of things. And we call them here, we separated chemicals present in high concentrations, caffeine, artificial sweeteners. I was just telling my students that we can actually track caffeine in our wastewater. And that's really interesting. Anyway, so yeah, and artificial sweeteners too. So they're really, really high concentration. So now that we're happy with the groupings of these chemicals, I want to walk you through, and I hope it's realize it might not be. Just follow my pointer. Hopefully that takes you to the right trend. So we went from, or they collected samples from BR1, BR2, BR3, all the way. And here I'm showing the data for upstream, where they get their water from, and then BR3, which now receives inputs from Nose Creek and Elbow River. So let's start with the BR1, which is the most upstream site. If you look at the concentrations, they're parts per trillion. So they're less than, I would say, close to less than 1,000 parts per trillion concentrations. And the concentrations upstream, interestingly, dominated by an antidiabetic, which is metformin. It's interesting, it's really only one compound that's dominating that, it's metformin. You also see, interestingly, some spikes of the red there, and the red, and also antibiotic in certain cases, which is the orange. So you see some seasonal spikes, which is interesting. So one hypothesis is the usage of that compound can also be seasonal, right? So tracers are the wastewater, the caffeine. If you look at the concentrations, they're still on the lower end, but we can detect them here at BR1, also at BR2. BR3, you see a little bit more spikes, so you see this difference in the trend, and the reason for that we suspect is coming from Nose Creek watershed, which apparently is a very dirty watershed. This watershed on its own, the sub-watershed, receives also sometimes sewage lagoons that would spill in certain occasions. So they know that this is sort of dirty, and that's why we see some spikes there with a little bit higher concentrations. So if we go further down to the BVs, Bonnie Brook, FC, and PC, Fish Creek, and Pine Creek wastewater treatment plant, you see them at a lot higher concentrations. So if you just look at the number of zeros there, it's way different than the ones that we have here. So you think 3 zeros, this one has 6 zeros. So it's really, it's much higher concentrations, makes sense, because it's the wastewater treatment plant at one. And if you look at downstream of BR4, you now see this sort of increasing concentration compared to the ones upstream. which really tells us that the concentrations here are contributed by these wastewater treatment plant effluents upstream. So we also found that it does seem to follow the trend in water. So remember I told you about solution to pollution is dilution? So that same concept of if you have high flows, you'll have low concentrations because you're diluting your contaminant. And if you have low flows, that's when you would have high concentration because now your contaminants are not as diluted. So that was an interesting trend because initially we thought maybe it is really just a seasonal, but it is tied to the water flows, which brings down questions to what happens when the river doesn't have enough flow. How can it actually assimilate some of these compounds in our environment? We just published this. I was very proud of this work. And if you want some technical information, I can send you a copy of that too. I have my email at the end of this presentation. If you want a copy of that, I can share that with you as well. No questions so far? Am I boring you all? It's very quiet. And I'm like, okay. So we talked about, okay, we find them in water. Do we find them elsewhere? Do we find them in sediment? Do we find them in fish? Do we find them in biofilms? Do we find them in bugs and insects? So this is one of the work that I did, I'm still doing. But this facility is from Pine Creek Wastewater Treatment Plant, and it has these 12 naturalized streams. So they're fake streams, they're man-made. And the idea is to test the fate and transport of different types of chemicals coming from a wastewater treatment plant, this fully operational treatment plant, or coming from pilot scale treatment plant. So the engineers, sort of a plug and play facility where, okay, I have new technology for wastewater. How does it work? Can it remove certain chemicals from our municipal wastewater? How does it behave in this aquatic environment? It's really a nice playground that most of my students have visited now. We go there quite regularly. So the streams also receive water from the Bow River. So it's not 100% effluent, it's 95% Bow River and 5% effluent. So typically that's kind of what you see. Really, in Bow River at least, the wastewater contribution can go up to 8% of the total flow. It's still low. I've seen places that can go up to 50, 60% contribution of the river flow is from sewage, treated sewage. So in a way, we're lucky in Canada to have big river systems that can assimilate, but I don't know if that's the way we should go. We should really think about what happens in the future. Yes, we have these big systems, but we really don't know how they're going to interact or how they're going to behave during climate change situations when you have droughts and whatnot. So what we did is, so this is, it looks like it doesn't have any plants. This is how it looks like now. So this is one of the streams that we sampled, one of my students collecting water samples. We also collected samples from the sediments, and we collected samples from the biofilm. So those are thin film of algae and bacteria that is present in rocks, that coats the rocks and other substrates. We also collected some biota, so we collected bugs and see if there's any contaminants in there. And we also collected some fish. There's a few biologists that are doing experiments. We're like, can we have some of your fish? Because we wanted to test if they have anything. They gladly gave us some fish. So did we find them? This is the work by Daniela Bulgarin, one of my master's thesis there. Student, she just graduated. She just defended her master's thesis. This is what she did for the last 2 years. So she collected samples from the sediments and also the streams and tried to compare them. So I'll walk you through the data very, very slowly. So you have these light green bars there from Canmore. So you imagine it's upstream, so you would expect it's cleaner. It doesn't have a lot of impact. You can see concentrations both in the stream and in the sediment quite low. But if you look at different types of effluent there, so you have the Bow River, already has high concentrations in sediment in the stream, And then if you add more effluent to it, 5%, the other one's 5%, the other one's 15%, you see an increase in concentration. So it's not new, right? Like you would imagine that if you have more wastewater load, obviously your concentrations would increase. So some of these chemicals here, I don't want to tell them if the name's venlafaxine, fluoxetine, that's venlafaxine, doesn't really mean anything to you, but these are antidepressants. And these folks right here are antibacterial, and carbamazepine is an anti-epileptic. So if you look at the antibacterials, you don't really see them in water, but you see them a lot in the sediments. So it really tells us that some of them would probably bound onto the suspended solids, and over time will settle out with the suspended solids and stay in the sediment. So when you look at water concentrations, it doesn't tell you the whole story. So we find some more contaminants in the sediment that settled out later on eventually. So that was exciting for Danielle. She's like, I found something in sediment. Is that a good thing or a bad thing? And then we looked at, okay, what happens in biofilms, in gammarids, and in water. So gammarids are just like shrimps, freshwater amphipods that live in the streams. So we collected these bugs, and also we scraped the biofilms in the glass flags or in the rocks, or from the rocks. And again, we looked at Canmore, Bow River, Pine Creek, treatment plant with 5% effluent, and Pine Creek with 15%. So venlafaxine is antidepressant, venlafaxine and fluoxetine. This is an antibiotic for methylprim, and carbamazepine is an anti-epileptic. So again, you see as the effluent increases, the contribution of effluent increases, you see an increase in concentrations in the biofilm. So even these folks actually accumulate some of these pharmaceuticals and personal care products. One thing that surprised us was the fluoxetine, which is an antidepressant, Prozac. So the concentration in the water is, when you think about it, 0 to 10, very low. But if you look at the concentrations in the sediment or in the biofilms, and also the gammarids, you see them really spike up, like really high concentrations. You look at the y-axis, the 300, this one is 80, this one is 4, this is 15. So this one here, they really love biofilms, and they really love sticking into the bugs as well. We also found some in fish. We're still figuring out the data sets for the fish, but we have some chemicals we also found in fish. They're in the muscle tissues. They're definitely lower, but we thought, okay, we didn't really look at the brain at that time because we got the tissue, and all the biologists took all the tissues that they wanted, and we just got the muscle tissue. So, but we found some of them also in fish tissues, and I'm not showing that one here. So, I kind of just want to cap this talk about, to understand what's going on. For me, as a water environmental engineer, we need to look back and see how we can address this legacy contaminants. There's different ways of trying to deal with them. You can change the chemical structure, make it more biodegradable so that it's not staying in the aquatic ecosystems or terrestrial environment. But we also need to look at today and how we as society functions so that we can manage the risk more effectively in the future. So it's sort of this chicken and egg, and I'm like, well, I don't have any options. I'm not telling those who want to take birth control pills not to take birth control pills. I think it has a huge importance in our society. But can we then create something that would be less harmful than what we have currently? But we're so good, and I think I have this hope that our society eventually will. We are known for our ingenuity, we are known for our problem-solving skills, and we're known for developing innovation. So hopefully we incorporate sustainability whenever we're creating these types of developments. They're key parts of society's development, and I just talked about here, if you have all of these chemicals, they go into the river, we see this fish intersects. Should we develop new products? Should we design new treatment plants? If water footprint is improved, would our energy footprint go up? So where do our priorities lie? So we want to make water as clean as possible, but then there's so much energy to clean water. Where do we draw the line? And of course it's not just a decision that an engineer can answer. I know I'm a piece of the puzzle, but I will not be able to answer that type of question. It depends on how society thinks of it as well. This is just some wonderful paradigm shift in wastewater that I am not doing, but a lot of the researchers are doing at the University of Alberta, is you think of wastewater as a resource. So it's a huge paradigm shift here where, okay, maybe we don't need clean water to water our plants, or maybe we can just use treated water from wastewater to use it for something else. Maybe the industrial processes don't really need clean water, so our toilet water is drinking water, quality water. Maybe we don't need that much energy for other types of uses. We can use them for irrigation, we can use them for recreational use, and we can even, in Singapore, because they have so much problem with water scarcity, they actually have really intensive wastewater treatment that is direct potable reuse. So wastewater, effluent, treated, and then it goes into drinking water right away. And they've done an amazing job. They're one of the biggest leaders in water reuse, followed by Australia as well, because they had to do it because of the drought. And Singapore is a small country, it doesn't have a lot of water resources. So there is that idea that we can do something with our wastewater and think of it as a resource. Others, there's certain sludge that comes out of wastewater, so the solids in the wastewater, a few folks are looking at potentially using them as a source of energy. So through anaerobic digestion, you can create biogas. You can probably use them as fertilizers as well, we call them biosolids. And in the wastewater, there's a lot of phosphorus. Maybe you can take the phosphorus out and use that sort of a gold mine for phosphorus. So there's a paradigm shift now in the field that, we're thinking about wastewater as a resource as opposed to just waste. So here we want to take out waste, and it's just basically just water. Another thing I wanted to point out is because I was born and raised in the Philippines, and Philippines is part of the global south. So if you look at, create this line maybe except Australia, because it's in the south, we see a lot of environmental problems in the global south. And the global north is really having a good quality life in terms of environmental health, in terms of public health as well. I was in the Philippines last year. One of the things that I wanted to do is go back to the Philippines where I grew up and do something now that I'm an assistant prof. And I was able to get a baby grant, a small grant. And but that grant let me go to the Philippines and collect some water samples and collect some fish samples there as well. It's one of those that required so much emotional labor, but it gave me the most satisfaction. This is their water. This is covered in algal blooms. I was stunned when we were there. It's a story that I have a few of my friends. I called them up. I did my PhD with them. They're all biologists. And I said, hey, I have this small grant. I can pay for your flight, but you have to take time off. And they all took time off, 2 weeks, to go with me. So they were the ones basically dissecting fish, and I was looking at water samples. And one thing that hurt me the most while I was doing that was we were in a tent. It was really, really hot that day. It was 37 degrees Celsius. And we were dissecting fish because we're collecting fish tissues, livers, gonads, and everything, the sex organs of the fish. And there's a group of children who were waiting for us and said, is there any fish that we can use for lunch today? Do you have any leftover fish that we can use for lunch? That broke my heart. Here I was just buying fish from local fishermen because we want to study them. There's some folks that couldn't even buy lunch. They're waiting for our research to finish so that we can give them fish to eat that day. So I want to go back. I will go back. We're processing some of our data sets from that. I have a few folks from the Philippines doing exchange. So we had a PhD student come to my lab and then worked with some of my grad students and processed some of the fish samples and hopefully going back there again to share the results with the community. Really broke my heart. But the reason that I wanted to say this is because if you look at our global emissions, the global north is responsible for 90% of excess carbon emissions. So it really, we have to go back and really focus on our society in terms of how we live. And I'm not saying that we all should become hippies. It's just a matter of, trying to think about what our actions are like on a day-to-day and see if there's anything there that we could change. And I shop. I'm not a saint myself. I'm also trying my best to reduce my carbon footprint as much as I can. But it is so painful that 90%, especially the global north, and those are former colonizers as well. And you go down and you see, okay, the impact of that is you go to these countries, get their resources. I was just in a watershed tour out in Nova Scotia, and they shut down their coal mining. And they said, so you still have coal-fired power plants, where do you get your coal from? You get it from Venezuela. So we, have these activities where we want to just live comfortably, but we don't know how other parts of the world actually truly live. So, and this brings me to this idea of whenever we're designing something, we really have to make it holistic approach. A holistic approach meaning that, before a lot of the things in engineering, for instance, are very siloed, and there's this increasing trend in incorporating sustainability into design, and many types of approaches. That includes, designing a product, like I said, is one of them, but really understanding what the life cycle of that product is going to be in the future. And by enabling this trend in sustainability, I just don't mean we need to improve this because it's more environmental friendly, but we also have to think about groups that are traditionally underserved and traditionally disadvantaged groups. So if you think about climate change, those vulnerable groups are actually more prone to climate change impacts than we are mostly in the global north. So, and is that because they were just bad? No, right? It's because of how we consume as a society and just how we think, and we just, I don't want to go and say capitalistic, but it's really, I'm part of that. I'm part of that line that buys things and then disposes some of them, and it really makes us think, and I'm not perfect myself, in terms of how we impact the way we live and how others also get impacted by those actions. So hopefully, I think we're trying to improve the curriculum in environmental or in engineering in general. There's a huge movement. Again, I was taught solution to pollution is dilution, and that's changing now. So hopefully we get to inspire different young minds in terms of approaching water issues in a lot different way than how I was taught or how the previous generations were taught as well. So with that, I'd like to thank a lot of grad students that have been part of my lab. I'm very happy that 3 of them graduated this semester. I have a couple more grad students that are here. They've been really fundamental in the work that I'm doing. And let's make waves together. Thank you so much for your time and for your talk.
What an amazingly inspired talk. I'm sure there's tons of questions. I'd like to go back to your slide for a second where you asked us questions about should we build new water treatment plants.
Oh,
can you slide back to
sure.
That's right there. Because I'd love to hear the folks in the room. What are your thoughts? Should we develop new products? Should we design new treatment plants? What will happen to our energy footprint? We've got some grad students in the space. We've got some sustainability scholars in the space. I'm gonna put you all on the spot. What are your thoughts on A, B, and C? You don't want me to start pointing, so someone speak.
It's a tough question.
Oh gosh, it is a
I
hard
don't-
question. You do not need to have an answer, I just love to know your thoughts. There are no answers that we can decide today. But coming up with these kinds of solutions, when we put it to a room, when we put it to a space, it's a great place to start building those conversations. So where do you see kind of the first step being, but while we let folks kind of think of their own thoughts?
Well, I'm not a water treatment engineer, so obviously I'm biased to water treatment. Unless, because I'm not a chemist, I'm also not a chemical engineer who creates products. I think if we can potentially develop sustainable water treatment, that might be a good way to go. I'm biased, obviously.
I agree, absolutely, yeah.
So I'm a chemist. So I actually think A is really hard for this, right? Like, it's hard enough to develop a drug, right? But to make a drug that is also going to decompose the way you want it to is maybe more challenging. But I was going to ask about B. Are people looking at, fermentation strategies, developing enzymes that can chew on these specific targets that we know are major contaminants and process them in a plant? Because that could easily fit into what you showed for plants, but I imagine it takes a ton of work to get that.
Well, thanks for asking. So the way that biological treatment are designed initially is environmental engineers, because we were initially sanitary engineers, which is deal with wastewater. They just really think of it as a black box initially. So you just put microbes in there, we know that they're aerobic or anaerobic, and then, remove some of these, perfect, let's do it. So now the trend in wastewater is really looking into those consortium of microbes, what type of enzymes they produce, and maximize those production so that they can efficiently remove certain types of micropollutants, or any type of pollutant. So micropollutants is really difficult because if you were a microbe, would you rather use big chunk of carbon like chocolate, or you want lettuce? So they would obviously prefer chocolate, which is, think about poop stuff. So that's chocolate for them. It's like Nutella in their bread. Whereas the micropollutants can also be degraded, but they're lettuce, so they would have those preference. So yes, but it's still debatable too in terms of which microbes actually eat up the micropollutants. So it's right now that there's a huge trend in microbiology that they're looking more in the consortium, and we're not biologists, so there's this overlap also in the training as well. I bet a lot of the environmental engineers probably know microbiology more than I do. Yeah, thanks for that question.
Yeah. Anyone else have any thoughts that they'd like to share? I won't point at you if you don't want to share. It's okay. But does anyone have any thoughts they'd like to share on this challenge?
Maybe I'll help you. So the only country in the world, started it, Switzerland, and it's one of the reasons why I moved to Switzerland. So, they're a rich country, they're smaller, but they're upgrading their wastewater treatment plant to deal with micropollutants. And the way is, they're a very democratic system. Everything, all of the legislation they have to vote. The entire nation has to vote. 70% of them voted, yes, I want clean water, I want you to design a treatment system that cleans water even though it's expensive. Because the way they were influencing the policy decision making is, it's only going to cost you 2 Starbucks a day. So are you willing to make that investment? They said yes, and they're willing to do that. So 70%, because of that, they changed the legislation. All of the major treatment plants have to upgrade it to remove micropollutants. So it hasn't happened in the entire world. They made a decision because they want to get rid of the pharmaceuticals and all of those types of personal care products, which tells us of how the society functions, can be also influential in terms of how they make decisions. On the other hand, in North America, even though they're intersect, they can actually still reproduce. So maybe it's okay. So let's not have regulations around this. Because a lot of my friends in biology, even fish have eggs, they can still reproduce. So that might be okay. Really? I mean, it's just like saying like only one person has cancer, so that's okay. No, of course not, right? Like, I think it's a different mentality.
Absolutely, no, and I think it brings up the point that it's not just the science, it's definitely the politics and the economics behind all these issues that make them a lot harder to address. Awesome. Well, the floor is yours.
Yes.
Does anyone have any questions?
Or comments.
Or comments, queries, conundrums, thoughts that they could share?
When you say personal care products, like what products are kind of the worst, like what's about them is really helpful.
There's thousands of chemicals, right? And there's only so much that the analytical instrumentation can detect. So antibacterial is one of them, so fragrance musk, like that can also be part of it. Sunscreen right now is huge in the city of Calgary because in their Glenmore Reservoir, people go. They're not supposed to swim there, but people are still swimming, and if you wear sunscreen, it's just going to go into your drinking water, source water. So sunscreen is huge. It's got some oxybenzone, which is found, or at least in lab studies, can be endocrine disrupting. So potential to feminize fish or masculinize fish. So females becoming males, so the opposite, fish masculinization. It's the opposite type of effects as opposed to fish feminization. So those types of things, there's still a lot that's unknown. Another area that it's difficult probably for many regulators is they happen in the occurring mixtures. So a lot of our studies are single compound or maybe two compounds, but what happens if you in a mixture, we don't really know the effect yet.
I have a follow-up question. So, are there any data if the organic cosmetics is better for this?
They're marketed as easily degradable, right? But
Yeah, but how much of it is real and how much is greenwashing?
yeah, I unfortunately, I'm not saying that we should not wear cosmetics or anything, right? I don't look at pills, birth control pills, but the concentrations they say are low enough to create an effect, and that's why in Europe, we have a few guidelines, but in Europe they have the Water Framework Directive that they really want you to make sure that the concentrations of hormones and diclofenac and a few other pesticides are below a certain threshold. So the reason for that is even if we use pharmaceuticals or makeup products or whatever, they are found in the environment, but the concentration is still not that high to create an effect. Whereas the birth control pills are very, very not toxic for the lack of a better word, but very potent. So those tend to be regulated more than the other chemicals, because otherwise you have to regulate thousands and thousands of chemicals. And there are new chemicals that are emerging right now, PFAS compounds, for alkaline, I can't even remember. Maybe the chemist can. So PFAS compounds that are found in Teflon, like just in your frying pans, they can release some of those chemicals. And they've been known to have some impacts in aquatic. The interesting thing is they develop them to be degradable in shorter chain, so that they're easily degradable, but they're so mobile. Like they're quickly moving to different compartments, so they spread really quickly, as opposed to certain things where they just sort of stay in the sediments or specific compartment. I know I didn't fully answer your question, but if I were a regulator, if it doesn't have that's the issue right now with regulators, mixtures, because we never regulate things in mixtures, the cumulative effects. So one compound, okay, well, that's low concentrations. Another compound is low concentration. But if you have all of them at high concentration, or in small concentration with additive, how do you do that? And the science is still figuring that out.
Yes.
Yes.
And so the birth control, there are differences, like you know differences between pills, patches, and then hormonal IUDs.
So the most studied one is ethinyl estradiol. It's the most potent. So if you have a female hormone, a natural female hormone is estrogen. That estrogen is, they say, has a potency of 1. The ethinyl estradiol has a potency of 2.5. So it's 2.5 times more potent than estrogen. The other hormones are, 0.3 times potent or 0.1 times potent, but the ethinyl estradiol is the most potent one of most of the ingredient in the active ingredient in the birth control. Did that answer?
Not really, my question was more about if I can make a choice which is better for the environment.
Oh, I see. Okay. Thanks. I can share you how I did it. I switched from a non-hormonal IUD. So now you know what my birth control is. Yes, I can share that. Sorry, camera. Oops. But I switched from a non-hormonal birth control, and that's copper-based intrauterine device.
Yeah, I know about it. I'm sorry, I know that about it. I heard it. It's not very dependable. No, it's
I'm not pregnant.
Many of this you don't want to share with the public, but it can also stay.
Yeah.
All topics are open.
well, I was told that it can make the period more painful.
Yes, it is. It's the price I pay.
Yeah.
Not taking hormones.
So if I don't want to pay this price between the home, so then there are only hormonal options.
Yeah, so right.
Are some of them better than the other ones?
I think at the moment is they haven't produced any type of alternative for birth control that similar to the birth control but no pain. And I think that's the price sort of I pay for, or others who make the decision, they know it's going to be a little bit more painful, the flow is heavier. It's not as regulated as the birth control pill that's hormonal, but it really goes back to, you have that choice and you have that option and choose. The choice is important and that choice should come from you. So it's hard, I can't tell others to do this and that because it really is their choice. And I choose to do a non-hormonal approach.
Yeah, but still between the hormonal doses, are there
Okay.
some that
The progesterone approach, that has a less, there's so many combinations. It's not as potent as the ethinyl estradiol. So that's those norgestimate and those types of things. Actually, I don't know them anymore. Thanks. I'm glad we're so open talking about that. I'm so. If you feel uncomfortable, I'm sorry.
Safe space.
Do you have, ideas or of methods of how the ethylene estradiol would be, removed from sewage?
I was going to say, bravo on being able to say that, because you've said it like 3 times, and I cannot repeat that. So bravo on
Ethinyl estradiol. E2.
There you go,
Yeah,
E2. That's what I'm going to go with.
So, advanced treatment systems, tertiary treated, which most Albertans have, are actually very good at removing ethinyl estradiol. So, if I didn't show the data here, the Calgary wastewater treatment plants have non-detects of hormones. It's good at removing the hormone. I should have said that, I guess. But yeah, we could not detect them. They're very low concentrate, like less than 0.5 nanograms per liter, 0.5 parts per trillion. So, and that comes from the biological treatment side of things. So some microbes, they think, and it's still debatable in the wastewater treatment world, is if you have a treatment that is long enough, if you let it sit in the reactor long enough, then you create a diverse group of microbes that now can eat lettuce instead of Nutella and bread with Nutella. So you have a more diverse consortia of bacteria or microbes that are potentially good at also using that as their food source. So tertiary treatment plants are known to remove them, and a lot of the treatment plants, our regulations in Canada says a minimum secondary. So obviously if you are a utility, if you're a town or city that doesn't have a lot of budget to upgrade, then you would go for the minimum that the standards require, right? So again, it comes down to this, it comes down to the decisions by these municipalities. Indigenous communities don't have water treatment systems. Most of them. They can't afford these types of, these centralized systems that urban settled cities have. So, and they're also very understudied. We don't even know what's in their water in many, or in their receiving environments, because we don't collect data from those places. So yes, so there are treatment systems that are capable of doing that. So tertiary treated usually.
So related to that, you talked about Switzerland is going to try and adapt their system to remove all micropollutants. Is that farther than tertiary? Is it even farther?
So they add ozonation, so and ozonation and activated carbon, which in our world here is only used for drinking water. So they're using technologies for drinking water to treat the wastewater. So they're willing to invest in that.
Just in terms of the economics, if we did increase the requirements for wastewater management in Canada, where is the budget? Like for municipalities who
Yes, that's a great question. I always tell my students in my water treatment class how our system is here in Canada. So we have the federal treatment by the federal government that says, okay, that's our mom and dad and parent, all of you provinces have this minimum guidelines that you need to deal with. Secondary treatment. Okay, perfect, I'll do that, mom and dad. And then all of the provinces will do their own thing. So they say, okay, well, we're going to set, these are the guidelines that mom and dad provided us, we're gonna make it more strict. So we say, okay, well, or less strict. So guidelines are not regulations. So there's no, like, I forget, I can think of a word, but there's no, if they don't follow the guidelines, they just don't follow the guidelines. They're not really, it's not, what's the term for that?
Enforceable?
Enforceable, yeah, or, so they can't get in trouble. So then, but the provinces say, okay, well, I can have it less strict or strict, but most of the time Alberta has stricter regulations than that of the federal. And then they say, okay, well, Alberta, all of you, my little babies, will have all of these level of treatment or whatever regulations or provincial regulations for your water. And now municipalities do it. So enact it. You're responsible for trying to make sure that the environmental levels or health protection is there, and also the public health is done. And you can use taxpayers' money for that. So a lot of the work comes from municipalities. So if municipalities don't have a lot of money, a lot of income, so they will just do the bare minimum, right? And they're fine. They are still okay, but they won't go above and beyond because they'd rather put that money for hospitals, for education. So you have a lot of sharks fighting for what is good for my specific community. So it's tough. So I always tell my students, you're only a piece of the puzzle. So if you go there, you're like, you probably, but it's up to us, right, to make that push if we want clean water, talk to our MPs, and that kind of stuff to have some political back. Yeah, municipalities, unfortunately. Yes, Al.
So we're seeing impacts on, or the collection of these pollutants in our fish, in our biofilms, in our sediments. Are we seeing an impact on humans yet? Is that something we've explored? Because that might convince people to pursue it?
So far the studies have shown that, so for instance, if you have anti-epileptic or anti-diabetic in your water needs you to drink thousands and thousands of liters of water for you to actually get the same therapeutic impact as that of an actual drug. So if you, and one of our collaborators in the city of Calgary calculated it, and I remember it being an absurd amount, that if you find the caffeine concentrations in the river, you need to drink so much water to be the same effect of caffeine in your Tim Hortons cup. So for long story short, right now it's showing that it doesn't have a huge impact in our human health. However, when you think about mixtures, that's when it can get a little shaky.
Yeah, sorry, just without questioning, I had another question, but just without question, I think I read a study that they found in the blood system microplastic.
Yeah. So that's another emerging classes of chemicals, and one of my students also just worked on the micro nanoplastics recently. Frida, she worked on that, and that was shocking. Because now you can actually find nanoplastics in the blood, and or in hair, and other in our human bodies. And the problem with nanoplastics is they're very small. So when they're small, they can actually cross some of the barriers, so the blood-brain barrier and other in our organs, and can create some sort of impact. And the big issue that a lot of the scientists are looking at is these plastics can be carriers of these micropollutants. So they can have, think of a Trojan horse effect. So they can carry with them a bunch of pollutants and then get unleashed once they're inside a specific organ. So it's still really, right now, the research is still ongoing for that one, to really.
And the comment that I have, and I would like to have your opinion, because from this three, the first one is kind of difficult sometimes because there are a lot of interest, like big pharmaceutical companies. So for the last two, I think, I don't know, what do you think about changing the paradigm in the concept of wastewater treatment plants and use them like biorefineries instead of like just a linear process? We are going to treat the water. That energy footprint is obviously going to go up, but what if we take what we have there? You touch a little bit on that, one group in Spain, they are using volatile free fatty acids from
BFAs,
to get the energy, to ferment, produce value-added compound, or what you describe about with the analogy of Nutella and lettuce. What if we only take the enzyme that eats lettuce? One group in Toronto, Biosome, they did a pool of enzymes to
and then and that has to work in both ways. So first, the challenge is not only it's supposed to be efficient for eating lettuce, it also has to be efficient in eating Nutella as well. So that is the challenge right now, is you're trying to create that, can it do both? And a lot of the focus is looking at either the enzymes or the microbial consortia that whatever's produced in that process, optimize it based off of that. Just in terms of upgrades, wastewater treatment plants and water treatment plants are the most conservative infrastructure because it works and it's great for, it's important for public health. Why do I need to mess with it? So unless they see that treatment has been proven at a full-scale level, then they definitely will create that confidence that, okay, I can break apart my system and start a new one. But it's a very, very conservative industry in making progress when it comes to designing new treatment plants. That's why it was not easy, but because most of the Swiss voted for 70% improvement, I want you to remove micropollutants. The wastewater treatment plants don't have any choice. The utilities don't have any choice but to find options that are currently available that are do full-scale assessment to see if it actually works. And it also means that you don't just destroy the wastewater treatment plant. Can it be a step that you can put in between, or after, or before? So that on its own will require a lot of testing. I don't know that was my opinion.
Because there are a lot of feedstocks there that we can like harness and use it for other things.
Mhm.
It would
Yes.
offset the
Yeah.
increasing the energy footprint.
Right. So another great example was when I was in Switzerland, our toilet separates urine and poop. So they would, because you don't use a lot of energy to deal with urine, but the poop can be used as fertilizers. So it's so weird because like go in there and have two different things and one goes that way and then the other one goes to the bottom and you're like, what's going on? And then that's one way also, just splitting your waste, and you don't need so much energy to deal with the one that is higher strength. And that, I think the Netherlands also are trying that approach as well. But it does that mean you have to change all of our toilets? Like it's you know, what are the incentives for people if you want to do that? So it again requires that survey or customer satisfaction if they're willing to do that.
Any last questions?
When we look at things in the food chain like mercury that bioaccumulate, do we see that with things like hormones?
So we see them in we haven't checked them in the biofilms, but the challenge with the hormone detection too is very, very difficult to analyze, and sometimes require so Calgary wastewater treatment plant or their treatment plant have that system, but not, it's such a difficult chemical to detect. But in terms of bioaccumulation, if you look at the property of the hormones, they can easily be transformed, right? So it really depends on, sometimes, you know, one hormone can be converted into something else, and that's the case for E1 to E3 or E3 to E1, E3 to E1 to the natural hormones. They've been observed in because these hormones, you don't know if those are natural hormones that, you know, if you go look at, maybe there's different in their structures too. So you have to be very careful in saying, okay, is that natural hormone or is it just a hormone from other parts or from us, from the wastewater? So I think the cows would have different types of hormones than humans, but they're still female hormones, they're still estrogens. So just maybe a comparison in both of